All right, the time is here. We're finally here. Um, we are going to talk about stoichiometry. Stoichiometry is a very, very important skill. This is going to be directly linked back to our very beginning of this semester talking about dimensional analysis because dimensional analysis is I shouldn't do blue. Let's do something more bold and forceful. We need to be using dimensional analysis correctly to be able to do this. So make sure you're good at your dimensional analysis skills. This is going to help us practice this. We already know 90% of what we need to know to be able to tackle these questions. Okay. Ultimately, what we're doing in stoichiometry is we're looking at the relationships between things in a chemical equation. Okay. So when we're interpreting chemical equations, we can look at this and we can say, okay, well, this could very easily be one molecule of nitrogen reacts with 3 molecules of hydrogen to give us 2 molecules of ammonia. That is perfectly reasonable. We could also say that this is 1 mole of nitrogen and 3 moles of hydrogen, and this is going to give you 2 moles of ammonia. Okay, that's also acceptable. Remember, moles and molecules are related by Avogadro's number, so these are the same idea. Okay, what we cannot do is we cannot say grams. Okay, this is not about grams. This is all about moles. Okay, so the best way we're going to be able to do this is we're going to use what we call a molar interpretation. Okay, the molar interpretation just means that the coefficients are going to tell us how many moles of each thing are in this equation. Now, because the formulas are tied together in the equation, and this equation is balanced, and the coefficients relate to moles, right? Remember, there's a 1 here. This is moles. Okay. You can make any conversion factor you want out of this equation, right? We could say, well, 1 mole of nitrogen is going to give us 2 moles of ammonia. We could also say that 2 moles of ammonia is going to need 3 moles of hydrogen. Or we could say that 3 moles of hydrogen is going to react with 1 mole of nitrogen. Everything is valid as long as we're pairing this coefficient with the formula. Okay, so we have to remember that this is in terms of moles, and we have to remember that we need to put formulas in the dimensional analysis. Okay, this is on top of already thinking about units and sig figs like we always do, and like we should be champs at doing those things by now. Okay, so let's see how this is going to work and put it into play. Over the course of the next several videos, we have a lot of examples of this to work through. We're going to work through problems together in class. I've got a lot of things for us to work on with this. This is a crucial skill that we have to be able to do. Okay, and so we're going to work our way through it. All right, here's an example. How many grams of sodium are needed to produce 9.63 grams of hydrogen? Okay, remember our dimensional analysis stuff, we want to find where to start. This is our good start, 9.63 grams of hydrogen, because it's the only piece of data we got, okay? And our answer then is going to be grams of sodium, okay? Because that's what we're asked to find. So now we have to remember our equation is always in terms of moles, and we have grams here. We're looking for grams and we have to get to moles. So this is going to be a couple of steps, right? We got to take grams of let me not do it over here. We got to take grams of hydrogen and turn it into moles of hydrogen so we can use the equation. Our moles of hydrogen using the equation will lead us to moles of sodium that we need, and then we can use the molar mass of sodium to figure out how many grams of sodium that actually is. Okay. All right, let's put this into practice and use our dimensional analysis. Really, the only new step is here. Okay. Everything else we've done before. Grams of hydrogen, 9.63 grams of hydrogen. Make a formula in there. Okay. We need grams of hydrogen on the bottom. Two hydrogens are 2.02 grams. 1 mole on top. Molar mass is always 1 mole. All right. Now, here's the new step. Our units tell us we need moles of hydrogen on the bottom so it cancels out. And we're looking for moles of sodium, so that dude goes on the top. Okay. Our coefficients are what go in here. So our coefficient here is a 1. So that's 1 mole of hydrogen. Here we have a 2 for sodium. So we're going to put a 2 right there. Okay. Now that we have the 2 there, we'll look up our molar mass of sodium and figure out that 1 mole of sodium is 22.99 grams of sodium. And we're done. Okay. Grams to moles to moles to grams. Okay. It's a very common pattern when we do this. In the end, we'll calculate this out, get 219.2017 grams of sodium. And hopefully you'll look at me and say that's dumb because I have the wrong number of significant figures. Maybe not dumb, that sounds judgmental. Uh, I'm not paying attention. How about that? We're not paying attention to sig figs, so let's do that. We want 3 significant figures because we're limited by hydrogen. And so this should really be 200. That looks horrible. 219 grams of sodium are needed. So this would tell us 219 grams of sodium should react and give us 9.63 grams of hydrogen. Okay, let's look at another one. Okay, how many kilograms of oxygen? So here's our answer. Kilograms of oxygen are needed to completely react with 571 grams of zinc sulfide. So this is our start, right? It's the number of things we're looking for. This answer is we're looking for oxygen, okay? I've given us the molar mass of zinc sulfide right here. So you don't have to calculate that out. It's given for us. Um, if you want to come up with a plan, we can come up with a plan. Our start is grams of zinc sulfide. So we're going to start with grams of zinc sulfide. Because we want to use our equation, this has to be used to moles of zinc sulfide. Okay. Once we have moles of zinc sulfide, remember we're looking for oxygen, so we can convert that to moles of oxygen. And using molar mass, we can get that to grams of oxygen. Okay. If we were looking for grams, we would be done. This is shit. Sorry. Crap. Then we're looking for kilograms, so we're going to do one more step and get this to be kilograms of O2. All right. Makes sense? Let's do it. I'm going to do a color change here. New outfit for a new era. I don't know. I'm losing my mind. Here we go. Okay, 571 grams zinc sulfide. Okay. Grams of zinc sulfide on the bottom. We know our molar mass is 97.48. Okay. This is for 1 mole of zinc sulfide. The 1 mole of zinc sulfide, so now we're here. We're going to moles of O2. That's our new step. We need zinc sulfide to cancel out. There's 2 of those in our equation. We're going to moles of O2. There are 3 moles of O2, so 3 on top. moles of O2. All right. Now we're going to grams of O2. 1 mole of 1 mu. Sorry, 1 mole of O2 is 1 oxygen is 16, so 2 oxygens is 32 grams. And now we need to get to kilograms. Do we remember kilograms? Remember, it's 1,000 grams is 1 kilogram. Don't get that backwards. We can put O2 here if we want to. You don't have to on that step, but the rest of it you do. Units, formulas, everywhere. Get it together. We got it. Okay. I'm running out of room, so I'm going to come over here and say this is 0.281165 kilograms of oxygen. Okay. Again, look at me, not paying attention to significant figures. -1 for me. All right. I would say sig figs. I probably should pay attention to what I'm doing. All right. Let's fix it. Uh, 3 significant figures because we're limited by zinc sulfide again. So 0.21. No, 0.281 units and formula, and there's our answer. Okay. This is the basics. Everything is going to feel similar. The devil is in the details. So a little things here and there are going to be different. So we want to pay attention as we're doing stuff. Um, I've got more videos coming that are more examples of a little bit deeper thoughts about stoichiometry and different things we can do. Um, so let me know if you have questions, and I'll catch you later.